What if the machine we built almost 50 years ago just told us something about the universe that we were never prepared to hear? Somewhere past the edge of everything we call home, a spacecraft the size of a small car is still awake, still listening, still sending faint signals back to Earth from a place no human plan ever imagined it would survive to reach. Before we go any further, hit like on this video, subscribe if you are new here, and share it with one person who still thinks space is boring, because after this, they never will again. In the spring of 2026, engineers at NASA made a decision that felt less like science and more like grief. They reached out across billions of miles and switched off one of the last working instruments on Voyager 1. It had been running since 1977, almost 50 years without a single day of rest. And now, on purpose, with steady hands, they turned it off. Not because it failed, not because the mission was over. They turned it off because the spacecraft is dying, slowly, quietly, and there was no other way to buy it more time. That single decision opened the door to something NASA insiders now call a make or break maneuver. A plan so delicate that if it goes wrong, we could lose contact with humanity's farthest reaching machine within a few short years. If it goes right, Voyager could keep whispering back to us well into the 2030s. But here is the part almost nobody is talking about. While engineers fight to keep this fragile old spacecraft breathing, Voyager is still doing its job. It is still measuring the space around it. And what it has found out there does not match anything scientists expected. The region beyond our solar system is not calm. It is not empty. It is not behaving the way any model predicted it would. This is the story of a machine, older than most of the people watching this. Still working, still discovering, still rewriting what we thought we knew about the darkness beyond our sun. To understand why this moment matters so much, we need to go back to where this story began. Back to 1977, a year before smartphones, before the internet, before most of today's scientists were even born. That year, NASA launched 2 identical spacecraft within weeks of each other. The reason had nothing to do with ambition and everything to do with timing. Once every 175 years, the outer planets of our solar system line up in a way that lets a spacecraft use each planet's gravity like a slingshot, flying from one to the next without needing extra fuel. Jupiter, Saturn, Uranus, and Neptune, all reachable in a single journey, but only if you launched at exactly the right moment. NASA took that narrow window. The result was Voyager 1 and Voyager 2, 2 twin explorers built to last just 5 years. Engineers expected them to fly past the giant planets, send back a handful of extraordinary photographs, and then quietly go dark, drifting forever through space with dead batteries and silent transmitters. Nobody expected what actually happened. The engineers who built these machines were not designing for legacy. They were designing for a single tight mission window, a handful of years, a handful of flybys, and then silence. There was no plan for what to do if the spacecraft simply refused to stop working. There was no long-term budget prepared for a mission that would still be running half a century later. Every extension since then has been improvised, decided year by year, sometimes almost accidentally, by people who never imagined they would still be managing this project decades into their careers. Voyager 1 finished its planetary tour by 1980. Voyager 2 kept going, eventually delivering the only close-up images we have ever captured of Neptune, a flyby so precise, so perfectly timed, that scientists still study it today. After that, both spacecraft turned their instruments outward, away from the sun, away from every planet, and pointed themselves into the unknown. And then, something remarkable happened. They just kept going, year after year, decade after decade. While entire generations of scientists were born, grew up, and joined NASA's mission control, these 2 machines kept flying, kept transmitting, kept doing science nobody thought was still possible. Today, Voyager 1 is almost 16 billion miles from Earth. Voyager 2 trails behind at roughly 13 billion miles. These numbers are so enormous that your brain cannot really picture them, so let's try a different comparison. Light from the sun takes about 8 minutes to reach Earth. A radio signal from Voyager 1, traveling at the exact same speed as light, takes nearly a full day to arrive. Think about that. If something goes wrong on that spacecraft right now, engineers on Earth will not even know about it for almost 24 hours. And if they send a fix, it takes another full day just to find out whether it worked. 2 days of waiting, of silence, of hoping for a single command. That distance, that loneliness, is almost impossible to imagine. And yet, through all of it, the spacecraft keeps moving, keeps measuring, keeps sending pieces of a puzzle back home that scientists are still trying to solve. Now let's talk about why time is suddenly running out, because this is the heartbeat underneath everything else in this story. Both Voyager probes are powered by something called a radioisotope generator, a device that turns the natural heat released by decaying plutonium into usable electricity. There are no solar panels out there, because sunlight this far from the sun is nearly useless. There is no way to refuel. The generators simply convert heat into power, slowly, steadily, and permanently declining. That decline has always been part of the plan, but by early 2026, the numbers had become impossible to ignore. Voyager 1's power output had fallen to less than half of what it produced at launch, dropping by roughly 4 watts every single year. 4 watts might sound tiny, almost meaningless, but remember, this entire spacecraft runs on barely enough electricity to power a small light bulb. Every watt lost is a choice that has to be made. Something has to be sacrificed to keep something else alive. For years, NASA engineers have been performing a kind of slow-motion triage, switching off heaters, cameras, and instruments one at a time, trying to stretch a shrinking budget of electricity across a spacecraft that refuses to stop working. It has felt at times like watching a patient slowly lose strength while doctors decide which functions matter most to protect. Then, in April 2026, a command was sent from a control room in California. It took almost a full day to arrive. When it finally reached Voyager 1, it shut down an instrument called the Low Energy Charged Particle Detector, a device that had been running without interruption since the day the spacecraft launched. Nearly 49 years of continuous operation, gone in an instant, not because it broke, but because keeping it running had become too dangerous. Just weeks before that decision, Voyager 1 had come frighteningly close to triggering its own emergency shutdown mode during a routine maneuver. If that system had activated, the spacecraft would have gone into a defensive lockdown, and recovering from it would have taken days, with no guarantee of success, given how weak the power supply had become. Engineers made a hard call. They sacrificed one instrument to protect the rest of the mission. That sacrifice is what bought time for the plan NASA now calls, almost with dark humor, the Big Bang. It is not a reference to the origin of the universe. It is the nickname for an incredibly risky power reshuffling maneuver, something that has never been attempted before on a spacecraft this old, this far from home, and this close to energy exhaustion. The idea is simple to describe and terrifying to execute. Engineers plan to shut down several systems at the exact same time and replace them with lower power alternatives, essentially rewiring how the spacecraft distributes its remaining electricity. Done correctly, it could free up just enough power to keep the last working science instruments alive well into the 2030s. Done incorrectly, on a machine with no way to be repaired, orbiting nearly 16 billion miles away, it could end the mission permanently. To reduce the risk, NASA is testing this maneuver first on Voyager 2, which has a little more power in reserve and sits closer to Earth. If those tests succeed, sometime around mid-2026, the same procedure will then be attempted on the more fragile Voyager 1. Nobody knows for certain how it will go. Every command is a gamble. Every reply takes a full day to confirm whether the gamble paid off. And yet, in the middle of all this uncertainty, in the middle of a spacecraft fighting simply to stay alive, something else has been happening. Voyager has been finding things out there that nobody expected. Things that are quietly reshaping how scientists understand the space between the stars. So what exactly has it found? For decades, scientists argued about where our solar system actually ends. Not where the planets stop, but where the sun's influence stops. The edge of an invisible bubble called the heliosphere, created by a constant outward flow of particles from the sun. Some early estimates placed that edge somewhere near Jupiter. Others pushed it much farther. Voyager kept flying and kept not finding it for years, longer than anyone expected. Quick pause. If you're the kind of person who likes learning things, most people never bother to look up. This channel is exactly for you, so tap subscribe now and turn on notifications, because what comes next gets stranger. Eventually, both spacecraft did cross that boundary. Voyager 1 broke through in 2012. Voyager 2 followed in 2018. And what they measured at that crossing point immediately challenged what scientists thought they knew. The first surprise was temperature. As each probe passed through this boundary, their instruments recorded plasma reaching temperatures between 30,000 and 50,000 degrees Kelvin. That is staggeringly hot, hotter than regions much closer to the sun. It sounds almost impossible, a wall of extreme heat sitting at the very edge of our solar system. Except that this region is so empty, so thin in actual particles, that this heat cannot burn or damage anything. There is nothing there dense enough to carry it. Still, nobody had predicted a thermal barrier like this, sitting right at that boundary, and yet both spacecraft measured it independently, years apart, in different directions. It is real, and scientists still do not fully understand why it exists. Some researchers believe it forms where the slowing solar wind collides with the incoming pressure of interstellar particles, compressing and heating a thin layer of plasma right at the seam between two very different environments. Others think it may be tied to turbulence building up at the boundary itself, energy piling up with nowhere else to go. Neither explanation is fully settled. What we do know is that this fiery, invisible wall sits at the very edge of everything we call home, quietly separating our solar system from the wider galaxy. The second surprise involved radiation. Inside our solar system, the sun's magnetic field acts like a partial shield, deflecting a portion of the high-energy particles that constantly stream in from across the galaxy. The moment Voyager 1 crossed the heliosphere's boundary, its radiation detectors recorded a sudden sharp spike, confirming that the spacecraft had left the sun's protection behind. That part was expected. What surprised scientists was the sheer intensity of it. Out there, in true interstellar space, Voyager is now being continuously struck by radiation that has traveled unimaginable distances, sometimes millions of light years, before finally hitting a small machine built by human hands. The environment beyond our sun's reach turned out to be far harsher, far more energetic than earlier indirect measurements had suggested. Our sun, it turns out, has been shielding us far more effectively than we ever gave it credit for, and we only understood the true scale of that protection once Voyager stepped outside of it and felt the difference directly. Then there is the density of matter itself, and this might be the strangest discovery of all. When Voyager 2 crossed into interstellar space, scientists noticed that the surrounding plasma was roughly twice as hot as their models had predicted. But the real twist came later, as Voyager 1 kept pushing deeper into this new territory. Instead of the density staying steady or slowly fading the further it traveled from the sun, it began climbing. Between 2013 and 2015 alone, measurements showed the surrounding particle density increasing roughly 40 times over compared to what was recorded just outside the boundary. Not a slow drift, a sharp, unmistakable rise. Scientists have two competing explanations. One theory suggests that particles from interstellar space slow down as they approach our solar system's boundary, piling up like traffic backed up at a toll booth, and Voyager is now driving straight through that jam. The other theory points to the interstellar magnetic field itself, suggesting that as it presses against our solar bubble, it pushes charged particles away from the immediate boundary and into a denser region just beyond it, a region Voyager may now be entering. Either explanation would have sounded like science fiction before Voyager actually measured it. Now it is simply data, sitting there, waiting to be explained. And then there is the sound, or at least the closest thing to sound that exists in a place with no air. Space beyond our solar system is filled with plasma, a thin sea of charged particles that can carry pressure waves in a way that is physically similar to how sound travels through air here on Earth. When Voyager 1's plasma wave instrument, essentially a long pair of antennas trailing behind the spacecraft, picked up something scientists were not expecting, a steady, continuous hum resonating through the emptiness. The discovery genuinely stunned researchers. Before this, the only signals detected out there were brief, sharp bursts triggered by solar eruptions, shockwaves rippling outward from the sun and eventually reaching Voyager billions of miles away. Useful, but rare and unpredictable, like catching a single flash of lightning in a storm that almost never happens. What scientists actually wanted was something constant, something they could measure continuously. That is exactly what this hum turned out to be. A steady, ongoing vibration in the interstellar medium, humming quietly at a consistent frequency, present whether or not the sun was active. Researchers who studied the signal described it almost like a single steady musical note, sustained and unbroken, but shifting ever so slightly in pitch over time. Not noise, not a glitch. A genuine, continuous vibration moving through the space between the stars, allowing scientists for the first time to measure density constantly. This discovery quietly changed how we study the space beyond our sun. It is the difference between only ever seeing a river during occasional flashes of lightning and finally being able to touch the water. Before we go further, take a second and think about this. Two machines older than color television in some households are still teaching us new physics from a place no other human creation has ever touched. If that is not worth a like and a comment telling me what surprised you most, I do not know what is. Alongside this steady hum, the one remaining instrument still measuring magnetic fields on Voyager has been adding another piece to this puzzle. The interstellar magnetic field was measured by Voyager 2 at a strength thousands of times weaker than Earth's own magnetic field. Faint, yes, but stronger than predicted. That extra strength matters more than it might sound. Our sun goes through an 11-year cycle of activity. During periods of high activity, scientists expected the protective bubble around our solar system to expand. During quieter periods, they expected it to shrink back inward. But when Voyager 1 crossed that boundary in 2012, and Voyager 2 crossed it 6 years later during a different point in that cycle, both spacecraft measured the boundaries sitting at almost exactly the same distance. It had barely moved at all. Scientists eventually concluded that the interstellar magnetic field outside our solar system was pressing back with far more force than anyone had calculated, holding our protective bubble at a nearly constant size. In other words, the shield around our entire solar system is being squeezed from the outside. All of this is being measured by machines that were never designed to survive long enough to see any of it. Today, in 2026, Voyager 1 has only 2 working science instruments left: the plasma wave detector and the magnetometer, tracking the invisible magnetic field surrounding it. Voyager 2 still has 3. That is all that remains of an instrument suite that once included cameras and spectrometers, slowly stripped down over decades to preserve just enough power to keep something still transmitting. And yet, these humble surviving instruments happen to be exactly the right tools for the questions of today. Everything we know about the space beyond our sun comes from indirect observations, telescopes looking outward. Only Voyager is actually out there. Only Voyager is physically touching this region, feeling its heat and its hum. There's a newer spacecraft now launched in 2025 called the Interstellar Mapping and Acceleration Probe. It orbits a stable point roughly 1 million miles closer to the sun than Earth, building detailed global maps. Combined with what Voyager continues to send back, scientists now have the most detailed picture ever assembled. We used to imagine the heliosphere as a smooth, simple sphere surrounding our solar system evenly. That picture turned out to be wrong. It is uneven, shaped by the direction our sun moves through the galaxy. Voyager is currently traveling through the compressed, turbulent wake left behind as our solar system plows forward. Whether the Big Bang maneuver succeeds later this year will determine how much more territory Voyager maps. The engineers behind this mission are not people who give up easily. If the maneuver works, both spacecraft could realistically keep transmitting valuable science well into the 2030s. If it fails, this remarkable chapter could close within just a few short years. Either way, the clock is running. What makes this moment in 2026 so remarkable is that some of the most important discoveries are happening now, using the weakest, most stripped-down version of these spacecraft that has ever existed. When they launched, each probe carried around 10 different scientific instruments to study the unknown. As decades passed and power steadily declined, instruments were shut off one after another. Cameras went first. Then came the ultraviolet instruments, each shut down, a quiet ending to another piece of scientific capability. And yet, almost as if by design, the instruments that survived turned out to be precisely the tools needed. It feels almost as if the mission somehow knew which tools it would need most at the very end. The steady hum, the rising density of particles, the unexpectedly hot wall of plasma at the boundary. None of these were things anyone planned to discover back in 1977. They are discoveries the universe handed us. Consider something else, too. When Voyager 1 crossed the boundary in 2012, it was pointed in a different direction. In fact, the 2 spacecraft are now so far apart that the distance between them is greater than the distance to Earth. And despite crossing the same kind of boundary, their measurements told 2 noticeably different stories. Voyager 1 recorded dramatic swings in the magnetic field. Voyager 2 did not see that same turbulence. Instead, it detected a thin layer of unusually hot plasma that Voyager 1 never picked up at all. This tells us the edge of our solar system is not a clean, smooth, perfectly even shell surrounding us. It is a complicated, uneven, constantly shifting boundary that behaves differently depending on location. Our entire solar system is sitting inside a structure being pushed, squeezed, and reshaped by everything surrounding it. Voyager 1 and Voyager 2 have given us exactly 2 data points along that enormous boundary years apart. And even with just those 2 points, the picture that emerged turned out to be far more complicated than predicted. Now think about how much of that remaining boundary has never been measured by anything human-built. What strikes me most about all of this is simply the fact that it is happening at all. We live in this moment. 2 machines, built before personal computers or the internet existed, are touching a part of the universe that nothing else humanity has ever created has come close to reaching. And what they find is new. The boundary is not the size we thought. Its temperature is not what we expected. The magnetic field is stronger. The density of matter keeps rising in ways our current theories still cannot fully explain. And running quietly beneath all of it is a real, measurable, continuous hum, a vibration moving through plasma. Every single day that these 2 spacecraft continue operating is another day of information gathered. Even if a new spacecraft were launched today, it would take at least 15 years just to reach Voyager 1. For the time being, these 2 aging machines are the only voice we have from the space between the stars. And that voice, faint as it is, traveling nearly a full day to reach us, is telling us something we cannot ignore. The universe beyond our sun is not empty. It is not silent. It is not a calm, predictable darkness. It is active, energetic, unevenly shaped, and constantly changing in ways we are only beginning to understand. Somewhere out there, almost 16 billion miles away, a spacecraft built in the age of rotary phones is fighting. It is still listening to a universe most of us will never get to hear for ourselves. Every watt is spent carefully. Think about everything that has changed since 1977. Empires of technology have risen and fallen. Entire generations have been born and never once noticed 2 small machines were still out there doing their job. And maybe that is the real story here. Not just what Voyager has found, but the fact that it is still looking. Still reaching, still refusing to go quiet, even after almost 50 years, outliving every prediction made about it. A machine supposed to last 5 years is standing at the edge of understanding, sending the unknown home. If this story moved you, hit subscribe so you catch the next update on the Big Bang Maneuver. This story is far from finished, and what Voyager finds next could change everything we thought we knew.